Okay, welcome to the Deep Delve. Today, we are diving into something really, really fundamental. Something we do every single day, often without even thinking about it. Measurement.
Right.
And we're not just talking about what we measure, but really digging into the how and maybe more importantly, why understanding the method actually matters.
That's exactly right. And for this deep dive, we've been looking at some notes and excerpts. They're from a resource aimed at technical high school students.
Okay.
And it gives a really clear, structured breakdown of the methods used in physical measurements. Some core concepts in there that are, well, surprisingly insightful.
So our mission then is to sort of unpack these ideas from the material,
Yeah.
pull out the key insights about the different ways we measure the world so that you, listening, walk away feeling, genuinely informed, maybe even appreciate that ruler a bit more.
Definitely. So at its most basic level, measurement is, well, it's how we figure out the size, the magnitude of physical quantities.
Right, and physical quantities are just properties of things.
Right.
Objects, substances, stuff you can actually measure.
Exactly.
And then express with a number and, crucially, a unit. Length, mass, time, temperature. Seems simple, but it's the absolute bedrock of physics, really.
It is. And the resource we're using breaks down the whole measurement process into, generally speaking, 3 stages.
Okay.
First, there's preparation, getting ready.
Right.
Second, the actual measurement itself, doing the thing.
The hands-on bit.
Yeah. And third, processing the results, making sense of the data you collected.
We're going to spend most of our time today on that first bit, the preparation and the different methods. That's the focus of our notes. But it's interesting they call out processing results as its own big step. There's more to it than just, plugging numbers into a calculator. Something for later, maybe?
Absolutely. That's a whole topic in itself. So let's dig into stage 1 then, preparation. It's surprisingly involved.
Okay, preparation. What does that really mean? It's more than just finding your tape measure, I assume.
Oh, much more. Preparation covers all the essential steps you take before you actually start measuring. And the goal is always to make sure you get the most accurate, the most reliable results possible.
Okay.
Given, what tools you have and what you're trying to find out.
And the materials stress that this isn't like a one-size-fits-all checklist.
No, not at all.
It depends heavily on what you're measuring, how precise you need that measurement to be, and, well, what equipment you actually have on hand.
Precisely. The source material highlights a few specific tasks as really crucial for good preparation.
Like what?
Okay, first, you need to understand the underlying physics, or at least the problem you're investigating.
Right.
If you don't really get what you're measuring and why, how can you pick the best way to do it?
Makes sense.
Second, you have to choose your measurement method, we'll get into the type soon, and really plan out your procedure, like step by step, meticulously. Third, you need to know your tools, your instruments. Be familiar with them, how to operate them correctly.
Seems obvious, but probably easy to mess up.
Oh, yeah. Improper handling. Big source of error. Now, here's a really interesting one the source emphasizes. You must consider the influence of the surroundings, conditions like temperature, humidity, maybe even radiation, depending on the measurement.
Where they use the example of temperature and thermal expansion.
Yes, exactly. It's a perfect example. Materials change size slightly with temperature. So if you're measuring, say, a metal rod really, really precisely.
Like super accurately.
Yeah. Doing it in a cold garage versus a warm lab could actually give you slightly different lengths, just because the metal itself expanded or contracted a tiny bit.
Wow, okay. So part of preparing is thinking, does the room temperature actually matter enough for this specific measurement I'm doing?
Exactly. It's about the required precision. If it does matter for the accuracy you need, then your preparation has to include a plan.
Like what kind of plan?
Well, maybe you need a temperature-controlled room. Or maybe you measure the temperature and apply a correction factor. Or maybe you need a different tool altogether, one that isn't affected by temperature as much.
Okay.
But if it doesn't significantly impact the precision you need for your purpose, fine. But the key thing is, you still had to think about it.
Right, it has to be a conscious decision, not just ignoring it and hoping for the best.
You got it. And then finally, part of preparation is actually analyzing the required precision itself, knowing up front how accurate your final number needs to be.
So you don't waste time getting way more decimal places than necessary.
Or the opposite, getting a result that's too rough to be useful. Defining that need for precision guides everything else, the method, the tools, the preparation steps.
Okay, so meticulous planning done. Now we get to the actual method. How does the source define that?
Pretty simply, actually. The method of measurement is just the specific way, the procedure you use to carry out the measurement.
And what determines which method you choose?
Well, the notes list a few things. The type of quantity you're measuring, obviously. Any physical relationships or definitions involved, like formulas.
Right.
And of course, the instruments you actually have available to use.
And the source material suggests we can classify these methods, put them into categories.
Yes, and these classifications are really helpful for understanding. The material gives us two main ways to categorize measurement methods.
Okay, what are they?
First, you can classify them based on how the method relates to the definition of the quantity being measured.
Definition.
That gives us direct versus indirect methods.
Direct versus indirect.
Got it.
Yeah. And the second way?
The second way is based on whether you need to know the value of that same quantity for another object or a standard to make your measurement.
Okay.
And that gives us independent methods, sometimes called absolute versus comparative methods, or relative methods.
Okay, let's unpack those. Direct methods first. What makes a measurement direct based on the source?
Okay, a direct method is one that's based either, directly on the definition of the quantity.
Like the formula.
Exactly, like the formula. Or it involves just a simple, direct comparison using a tool that measures the same property.
Can you give an example based on the definition?
Sure, let's use density. Density is defined as mass divided by volume, right? Porosity is mv.
Yep.
So a direct method would be measure the mass using a scale, measure the volume, v, maybe by seeing how much water it displaces, or using geometry if it's a regular shape.
Okay.
Then you calculate density using that defining formula. You measured the parts of the definition directly.
And the comparison example, like the ruler.
Exactly like the ruler. Measuring length with a ruler or a tape measure. You're literally placing the object alongside the markings on the ruler. You're directly comparing its length to the standard units marked on the tool.
Got it. Simple enough. So if direct uses the definition or a straight comparison, indirect must be different.
Precisely. Indirect methods figure out the quantity you want by measuring its relationship to other quantities. Often, quantities it isn't directly defined by. A lot of the time with indirect methods, you're actually measuring an effect or a consequence that's caused by the quantity you're interested in.
Okay. How would that work for density then? An indirect way.
Good question. Using Archimedes' principle, that's a classic indirect method for density.
How so?
Well, instead of measuring mass and volume directly, you might measure, say, the buoyant force acting on the object when you submerge it in a fluid.
Okay.
Then you use a known physical relationship, one involving that buoyant force, the density of the fluid you used, gravity, things mentioned in the source material to calculate the object's density.
I see. You're not measuring mass and volume, you're measuring the buoyant force.
Which is an effect related to the density.
To figure out the density. Got it. Measuring the outcome, not the definitions part.
Exactly. That's the core idea.
All right, that distinction makes sense. Let's move to the second pair. Independent or absolute methods. What's the key there?
With an independent method, you get the value of the quantity directly in the units you want. And the crucial part is, you don't need to know the value of that same quantity for some other object or standard to get your result.
So the measurement kind of stands on its own.
That's a good way to put it. Think back to our direct density example, measuring mass and volume.
Yeah.
That's also an independent method. You measure the mass of your object, the volume of your object, and calculate its density. You don't need to know the density of, say, water or some standard block to do that.
Right. What about using specific tools?
Using a modern digital scale for mass, that's independent. You put the object on, it tells you the mass in grams or kilograms, done.
You don't need those little standard weights.
Exactly. No comparison needed. Or using an ohmmeter for electrical resistance. You connect the leads to your resistor, it shows you the resistance in ohms. You didn't need a reference resistor with a known value. The tool gives you the value independently.
Okay, so I'm guessing comparative or relative methods do need that reference value.
You got it. Comparative methods give you a value that's relative. It's essentially a ratio comparing your quantity to the same quantity of another known object or a standard or even the medium it's in.
Like the Archimedes density example again. Is that comparative too?
Yes, it is. That indirect method using buoyancy is also comparative.
Why?
Because remember, to calculate the object's density from the buoyant force, you absolutely have to know the density of the fluid you submerged it in.
Right. You need the density value for something else.
Exactly. You need the value for the same quantity density, but for a different substance, the fluid, to act as your reference point.
And the old-fashioned balance scale.
perfect example of a comparative method for mass. You put your unknown object on one pan.
And add the little weights to the other side.
Right. You add weights with a precisely known mass until it balances. You're directly comparing the unknown mass to the known masses. You need to know the mass of something else, the weights, to find your object's mass.
Okay, I think I've got those two pairs straight now. Direct versus indirect is about how you relate to the definition.
Definition or effect.
And independent versus comparative is about whether you need a reference value for the same quantity.
You've nailed it. And the source material actually ties this together nicely with some examples showing how one method can be, say, direct and independent, or indirect and comparative.
Like measuring electrical resistance using Ohm's law.
Yeah.
R equals U over I. You measure voltage U and current I.
Right. The notes classify that as a direct method because you're using the defining relationship, Ohm's law.
Okay.
And typically, when you use something like a multimeter or an ohmmeter to measure U and I for your specific component, it's independent. You calculate the resistance without needing to compare it to another known resistor.
What about measuring speed? Like measure distance S and time t, U z vis t.
And that's direct because you're using the fundamental definition of speed.
Makes sense.
And it's independent because you only care about the distance and time for that specific object's motion. You don't need any other speed information.
The notes also threw in some indirect examples, didn't they? Like finding g, gravitational acceleration, with a pendulum swing time.
Yes, or measuring temperature based on how much something expands, like in an old mercury thermometer.
Right.
Those are indirect because you're not measuring gravity or temperature directly by their definition. You're measuring something else, the pendulum's period, the length change.
An effect.
Exactly, an effect. And then you use other physical laws or relationships to infer the quantity you actually want.
Okay, this leads perfectly into the task from the source.
Yeah.
Measuring a car's speed. Two methods given.
Yep.
Method A, measure a set distance, time how long the car takes to cover it. Method B, use a radar gun. How do we classify these?
Okay, method A, using distance and time, VSST. We just said that's direct because it uses the definition. And it's independent because you only need the distance and time for that specific car. No other car's speed matters for this calculation. So method A is direct and independent.
Okay, what about the radar gun, method B?
The radar gun is classified as indirect.
Why indirect?
Because it doesn't measure distance and time in that VS sense. It sends out radio waves and measures the frequency shift of the waves bouncing back. That's the Doppler effect.
Yeah.
The source doesn't go deep into the physics, but the key is it's measuring and affect the frequency shift to figure out the speed. It's not using the SAS definition.
But is it independent or comparative?
It's independent. The radar gun gives you the speed of that specific car it's pointed at. It doesn't need to compare it to another car or know any other speeds.
So the radar gun is indirect and independent. Interesting.
Yeah, that comparison really shows how the classifications work. A method fits into one from each pair.
So let's bring this back home. Why does understanding these distinctions, direct, indirect, independent, comparative, why does this matter for you listening right now if you're not, timing pendulums?
Because measurement is just everywhere. It's woven into daily life so fundamentally.
Yeah.
Think about it. Baking a cake. You're measuring ingredients, and precision there can matter a lot.
Oh yeah, too much flour. A disaster.
Exactly. Or a DIY project, measuring wood for cuts. Or even just estimating travel time. You're constantly using measurement principles, even unconsciously.
Right. And thinking about that preparation stage we talked about, it suddenly makes sense why things go wrong sometimes. Did I grab a measuring spoon when I needed a scale for more accuracy? Did I think about whether the liquid was hot or cold when I measured its volume? Did I even read the tape measure right?
Exactly. That preparation mindset is universally useful.
Yeah.
And understanding the methods, direct versus indirect, independent versus comparative, it gives you a deeper insight into how the tools you use or the techniques you employ actually arrive at that number.
It's not just magic.
No. It moves you beyond just accepting the readout. It helps you think a bit more critically about the result, its potential accuracy, what it's really telling you. It adds a layer of understanding, whether it's a kitchen scale or reading a scientific report.
So, okay, we've covered a lot. The stages of measurement, focusing on that really vital preparation step, thinking about environment.
Yeah, the influences.
And we've unpacked these key classifications for methods, direct versus indirect.
Based on definition or effect.
And independent versus comparative.
Based on needing a reference or not. Using some good examples from our source material. And as those sources hinted, the story doesn't stop once you have the number. The next big step is processing those results. And crucially, dealing with the fact that every measurement has some error, some uncertainty.
Yeah, nothing's perfectly exact.
Nothing. And dealing with that uncertainty is critical. Something the source material seems to be heading towards next.
Which leaves us with a really interesting thought to chew on, doesn't it? If every single measurement, no matter how careful the prep, no matter how sophisticated the method, always has some level of error or uncertainty built in, and the method we choose influences that uncertainty, what does that really tell us about the facts and figures we encounter every single day? In science, in the news, in data reports, everywhere. Something to maybe ponder until our next deep dive.